Synthesis of transition metal alkyls. If you had tungsten hexachloride and you wanted to make a tungsten alkyl complex, how would you do it? By comparison to the main group chemistry that we learned, if you wanted to make a transition metal alkyl complex from the metal halide, how would you do it? You can have insertion into metal hydride bonds, so you can insert an alkene into a metal hydride functionality. Oxidative addition. You can take an alkyl halide and oxidatively add. Now, what is oxidative addition? Oxidative addition is the opposite of reductive elimination. So oxidative addition is where you take an element and you add a metal alkyl, an alkyl halide to it, and you make a new metal carbon and a new metal halide bond. Your coordination number increases by 2 and your oxidation state increases by 2. We call that an oxidative addition. But the most common way I'd expect you to be able to do this is this way, through metathesis. So if you're asked for a model way of making a transition metal alkyl, I'd expect you to come up with syntheses that look like this. So we just start with a metal halide and a more electropositive organometallic reagent, so a Grignard reagent or a diorganomagnesium or an organolithium reagent. We do a metathesis, which means exchange. We eliminate lithium or magnesium chloride and we make a new complex. Now you will note that we have a titanium tetraalkyl compound there. That's not a mistake. There's something special about this titanium tetraalkyl compound that means that it is actually stable. So we can do the same sort of thing with tungsten. Remember, any more electropositive organometallic reagent will do. So trimethyl aluminium is reactive enough to alkylate tungsten hexachloride in this system. Here we're using methyl lithium or an alkyl lithium in order to make a metallocene alkyl species. Most of the compounds that you will encounter at this level are 18 electron complexes. So those two that we saw first are 18 electron complexes. However, it is not always possible to reach 18 electrons. So this will stretch your pieces of paper. What is the electron count of this complex? Let's do the one on the right-hand side. So this is the trimethyl methyl complex of titanium. What is the electron count of this titanium complex? Okay, all right, so that's an 8 electron complex. So 8 is easy enough to do, I guess, because we had a special extra one on there. So that's an 8 electron complex. What does 8 electrons say to you? 8 electrons should say to you, this is a spectacularly electron deficient compound. I bet that's really reactive. It is really reactive, but the reason it's stable at all is because these really fatty trimethylsilyl groups produce an umbrella of steric protection for the metal center. If this was just a methyl group, it wouldn't be stable. With a trimethylsilyl methyl group, then this is just about stable. It's very reactive, but we can isolate it, we can do chemistry with it. Now, if we want to produce something even more electron deficient, then we need to use an even more sterically encumbered alkyl ligand. So this one will require some innovation on your part. What's the electron count of the complex on the left? This is a 7 electron complex. Now that should be screaming at you. 7 electrons. Not only is it spectacularly electron deficient, it's got an odd number of electrons. This species has got no right to be stable, and yet it is isolable, and the reason that it's isolable is because we've got these whacking great bis trimethylsilyl methyl ligands producing a steric umbrella and stabilizing the complex. So if you use a bulky enough alkyl ligand, which incidentally, neither of these have got beta hydrogens. Beta hydrogens still very much a no-no in these systems. If you use a bulky enough ligand without beta hydrides, then you can produce these very electron deficient metal alkyl complexes.